respected audience. Today's talk is a heat exchanger fouling mitigation by environmental friendly additives. So additives are there, have to be the environmental friendly. So that is the subject matter. And I belong to this part of the planet. And then from here, I moved to Malaysia here in 2009. And since then, I have been working in the University of Malaya as being a tourist out here. So this is me. And then today we will cover the introduction, motif, background research, all these things in the background of the fouling mitigation. So the heat exchangers are extensively used in industrial sectors as well as household refrigeration and everywhere. So with the advancement of science and rapid growth of industries, the power consumption increased and the energy consumption also. So to make this quick challenge of the energy demand, these non-replenishable and replenishable energy sources are being used. So in this case, as the growing energy consumption is escalating the growth of energy consumption, so that the researchers and scientists and industrialists are concerned about the transportation of energy as well as the recovery of energy, so that these heat exchangers are used specifically for that purpose. But in course of time, when the heat exchanger is used in the industries, in course of time, it gets the deposition from the cooling water, and that is dissolved salts from the cooling from the water, the surface water, or the groundwater, which is being treated to make it cooling water. There, the dissolved salts deposit on the heat exchanger surfaces due to difference in temperature. The temperature, most of the dissolved salts, if they are inverse soluble in characteristics, they are responsible for this deposition. So with the increasing in the surface temperature, the solubility decreases so that it deposits on the surface. You can see that the different types of deposits being observed on the different heat exchanger surfaces there, mainly calcium, magnesium, or the salts of carbonate and sulfate salts. So we find that this deposition incurs the cost due to the unprecedented shutdown of the plant, as well as the production loss. And most of the countries, there is a huge percentage of, some percentage of their GDP and GNP is lost due to this fouling. So the researchers tried to mitigate it, and then since long people working on it, and then we have also started the work in University of Auckland, and then after that in 2009 started in University of Malaya going on. So there are different sorts of fouling on the heat exchanger surface: crystallization, particle, chemical corrosion, biological fracture of the system. So regarding the mechanism of it, the crystals, the cation and anions of the crystal, these deposit salts, they are attracted due to on the surface of the higher temperature surface, due to the temperature rise, the solubility decreases, and they are attracted due to electromagnetic force on the surface, and then form the crystals on the surface. And in course of time, there is crystal deposits on the surface, and then due to exfoliation, due to shear stress on the surface, then the exfoliation occurs, and then some percent is removed and again deposits. So this breaking and making is still going on continuously unless it forms an asymptote there or a steady state. So in some cases, the steady state at a very high resistance creating, and it loses the heat exchanger efficiency and performance. So that this type of fouling, and the crystallization and particulate, this type of fouling, it creates the resistance, and then we need to either go for the shutdown of the plant or need the maintenance of the plant. So that could be done by unprecedented shutdown. And as we mentioned there, that it is needed to meet this challenge, different measures being taken. So some modified the process parameters, and then some also changing the surface, and some adding additives. So we'll concentrate here in the case of the additives and surface alterations or the coatings, how it can be mitigated. So we find that for this, we try to do this experiment, and this experiment being done in the experimental setup. So one of the setup, we find here that this is the test section, and then the hot water flowing through this for raising the surface temperature at a high level, and the solution remaining outside of it, submerging this test section, so that when the surface temperature gone up over there, then the solubility of the dissolved salts reduces, and then it deposits on the surface. So this the work is being done here with the supersaturated solution. But in nature, in the heat exchangers, it takes time to deposit on the surface. So to get this study done within the stipulated time, the supersaturation of the solution is prepared. So this is another setup, and then it's annular and different setups. We have several setups to do this type of experimental test run. So as it's difficult to dissolve calcium sulfate and calcium carbonate in the water, so it's being done on the reaction. So it's being reacted with the nitrate tetrahydride plus sodium sulfate, calcium nitrate tetrahydride, and then sulfate is being formed. Similarly, chloride and sodium bicarbonate and carbonate is formed there. But the sodium chloride here is not doing anything because it's a normal soluble source. So that's how this work is being done here. And then in this experiment, we can see that the solubility decreases with the rise of temperature. This is the calcium sulfate, disulfate there. So we move on further there. These are the equations we use there for calculating the heat transfer resistance and the fouling factor. So in course of time, we find that when the deposit on the heat exchanger surface, so we get this type of deposition there, and it's depending on the thermal conductivity of the surface, the deposits changes. So we find that if the surface is more conductive, then more deposition there. So aluminum and then the brass and aces, according to their conductivity, the deposition being recorded, and the effect of concentration. If the concentration increases there, the solution, then more deposition, temperature more there on the surface, more deposition there. But the biggest challenge is that when there is deposition on the heat exchanger surface, it doesn't come along, rather it introduces their corrosion. So that problem, due to that problem, fouling run cannot be reproduced. So we have to change the specimen to get into the initial state. And we can see here that how this surface changes with the deposition on this. So we find here there are different ways of the mitigation, that the cleaning and then mitigation and cleaning there, because when it is deposited, I have to clean it, chemical, and then modifying the plant conditions and electromagnetic field as surface treatment, and introducing additives and surface coatings. So concentrate on this the last one. So here we find that one of the experiment being first done here by adding the natural additives there, such as the gum arabic, and it was found very positive results in 2010, 2011, something like 2011 or 12, something like this. Then it is being reported. So we find here that not only the natural polymeric additives, rather the nanoparticles people being used it since 20 years, a long time ago, for the heat exchanger performance enhancement, adding it to the heat exchanging liquid, and then try to enhance the performance of the heat exchanger. So the same experiment research being done in this University of Malaya, and the same liquid the same particles can be used for the fouling mitigation. So long time ago, the particles being used for fouling mitigation, that was bigger 30 years back there. But now that is difficult to handle, and that's damaging to the equipment. So if the nano-sized particles being used, then it can return to the fouling mitigation and without damaging the equipment. So with it, we move on further there, that for preparation of the nanoparticles, there's different methods being used there. So here we'll just focus on some of the things what is being done here in the laboratories. So when we prepare these nanoparticles, and then it can be obtained from the commercial basis. So once this particle is being prepared, and then it needs to do functionalization for the suspension of it. So that functionalization is done either by the acid method or the bio-based. So currently, the scientists are more interested on doing to protect the environment and do it on the basis of bio-based. So here the research was done also on the basis of it, the bio-based functionalization, and it can be seen that the natural the extract from the natural products, that is, you can see the cloves or these gallic acid or neem or other plants, plant extract being used for the radical reaction with this by introducing the covalent functionalization in the surface on the particles. So it gets from the hydrophobic, it transformed to the hydrophilic with the addition of the OH, when one of the reaction being shown here. And then another method is adding surfactant. So if the surfactant is added, then we get the problems there, it reduces the conductivity. So we can see that due to this functionalized carbon structured nanoparticles, so we get their heat transfer coefficient higher, and then when it is applied in the fouling mitigation, then we'll see that it reduces the deposition on the heat exchanger surface at a considerable manner. So here, there's not only this carbon structure, but also the oxides of metals and their binary or tertiary composition. These composites can also be used for fouling mitigation. So here we can find that with the enhancement of the temperature and with the enhancement of the concentration is being enhanced, and then concentration of the additives we're talking about, that the deposition is reduces. So this is the case of some of the materials used for the retardation of fouling being presented here. This can be, here we see that these different metal surface get the different sorts of deposition there. So now we see the additives. If it is added a long time earlier, it is a sequestering agent, and then if it is added to the heat exchanger, then it reduces the deposition on the surface when it is added to the fouling liquid. But if it is the multi-well carbon nanotube structure is being added in this experimental case, and then we find also it reduces the deposition, but it's highly corrosive. So that is why have to find some other fluid there. So if it is a DTP, this functionalized, then nanoparticles are used of the same multi-well carbon nanotubes, then this deposition, fouling deposition is reduced there, and we get the equipment surface not being damaged there. So that study enhanced our research in that specific field, that where we get the percentage of retardation higher, as well as the heat exchanger surface will not be affected much. So the results are being shown here that if it is DTPA, there's the polymer there is being used, then we get the very low level of deposition on the surface. Rather, in some other cases, we get higher. So this way, once it is explored, then it can be used for the fouling mitigation and will be finally recommended. So when we come to the mitigation of mineral salts using bar-based functionalized graphene nanoplatelets, then it is also found that the heat exchanger increases as a heat transfer coefficient increases, as well as the fouling mitigation is noticed there. From this result, it can be seen. So we go further over there, then we see that not only the particles of the metallic or functionalized nano, rather also the cellulose and the cellulosic particles of the bigger size, as well as the nano size, can also be used for the fouling mitigation. These are the natural means of protecting the environment as well as the mitigate the fouling. By the way, we find that most of the chemicals available in these commercially, many of them are not environmental friendly as well as carcinogenic in nature. So that is why the carboxyl methyl cellulose (CMC) and cationic aniline polymer and polyallylamine hydrochlorides. These are the in this way. These are, as well as the particles, the carbon structured particles, and then metallic particles, nano size, and then the cellulosic materials are also used for the fouling mitigation. So in this case, we see that if we use the natural fiber, then it helps the fouling mitigation by a considerable amount of reduction is noticed in fouling mitigation. Because if we increase the fiber particles smaller in size, say 2 millimeter, and then this concentration is 0.1%. If it is in the solution, then we get almost no fouling for a long period of time. So if it is 0.1, then about 40 days, there was no fouling there. But if the concentration is reduced, then we get fouling, but much lower than without any additive in the fouling solution. So this data indicates us that it can be used for mitigation of fouling there. So in different test sections is being tested and found that in most of the cases, the same results is being observed. So with this analysis, it can be seen that the fouling mitigation can be done with the cellulosic and this polymeric fiber as well. So not only the natural cellulosic fiber, also the polymeric fiber can retard fouling. So this is some of the view of the deposition of crystals on the fouling surface, heat exchanger surface, and then the retardation on the heat exchanger surface, as well as the fibers is by scavenging the surface, as well as by affecting the boundary layer. And these eddies, it affects the boundary layer of the heat exchanger surface, as well as the effects the eddies and returns the deposition on the heat exchanger surface. So with this understanding, it can come here that not only induction time, if we call the induction time here, then it not only it reduces, but with the increase of concentration, it remains a longer time without any. And then as it is biodegradable, it can be screened and taken off from the solution and thrown to the nature. So it will be perished in the nature. So with this understanding, we can find that if it is natural and if it is polymeric, both of this biodegradable polymer can be used for the fouling mitigation approach. So we move on further there, then it's found that if it is the polymeric, then we also get the similar effect as being presented here in the slide. So we move on further there that the non-woods also can be used, non-wood fibers. So wood we get from the trees, and the non-wood we get from the kenaf, grass. All these fibers can be used for this purpose. So now move on to the coatings there, and we see that in many cases, the surface alteration by adding coatings or by modifying the surface by different means, it can also be returned to the rate of deposition here. So we find that if the total surface energy is less than the less deposition there, if the contact angle of the surface is greater than 90, there is a higher contact angle there, that means it's more on hydrophobic in nature. So it returns to the rate of deposition on the surface. So in this case, different polymeric and the polymer and metallic composite coatings being applied for the retardation of fouling on the surface. So some of the procedures being mentioned here. And then in this case, by adding the graphene coating, polymeric graphene coating on the surface composite there, then we find that the only 14% of the these deposits on the surface is being noticed in comparison to the without any coating. So more research work is going on in at this time in the University of Malaya by exploring the polymeric sources for fouling resistance coating, so that if it is conductive polymeric, then it can be used. So another research we explored here that with the addition of surface coating with the composite, it can also reduce the resistance and prolong the induction time, so that the heat exchanger can withstand longer time. There's another coating results being shown here. So all the cases we find that it reduces the deposition on the heat exchanger surface. So finally, we see that the green chemical additives provided successful mitigation and among the coatings, the conductive polymeric coatings, and the composites, which can keep the heat transfer resistance a lower level, and the surface deposition will be retarded, can be possible to develop with the procedures being mentioned here. And this, we move on further. There some of the research work being done in this university in these specific fields. With this heat transfer augmentation being studied there, and the fouling mitigation being studied there, particle characterization also done in our labs, and then is the functionalization of nano being done over there, and the solar energy harvesting also, and as well as the paper pulp, that is the fiber particle characterization, improvement of the paper quality. This way the work is going on. So at the end, I'd like to thank the Vebleo webinar on science, engineering, and technology management, and for conducting the research work in our labs, the grants being given by the different authorities, and to the researcher of the advanced CFD lab and fouling mitigation lab of the University of Malaya, and you, the Mr. Chairman, and to the audience for listening to me. Thank you very much. With it, I have come to the end.